right, so hi everyone, and welcome to today's True Talk. Today we'll be having Emma, who is a PhD student in machine learning. She's also a Churchillian. She's actually doing a research that's an interface between machine learning and clinical medicine. We're going to have her talk to us today about some algorithms she's done with the intensive care units. Yeah, go on. Thank you.
Okay, cool. I share my screen now. Okay, can everyone see that?
Yeah.
Okay, perfect. So today I'm going to talk a little bit about the recent project that I've been doing, and this is in collaboration with Microsoft. And we've been looking at different ways to model the length of stay prediction problem in the intensive care unit. So this is particularly pertinent right now with the coronavirus, because one of the things that we want to make sure that we can do is really streamline the process of sending patients to through the hospital to make sure that they're not building up in the intensive care unit. So first of all, I just wanted to check. Actually, no, I will just assume that it's I should make it for a general audience. So here's the overview of the talk. So I'm going to start with explaining a little bit about length of stay prediction, why it's an important problem, and a bit about how machine learning can help us with solving it. And then I will talk a bit about the data itself. So the electronic health records, which are data that are stored in hospitals and collected by doctors. And a bit about why they're difficult to work with machine learning. And then I'm going to explain our model architecture and compare it to more established methods for modeling time series. And then I'll talk about the results. So why do we care about length of stay? Well, first of all, it's really important for hospital expenditure. So actually about 85 to 90% of interpatient variability in hospital costs is purely down to how long they're staying in the ICU for. The other thing is that the longer the patient stays in the hospital, the more likely they are to catch a hospital-acquired infection. So at the moment, this could be coronavirus, but also in more normal times, we also worry about things like MRSA, which is multiple drug-resistant bacteria, which can be very difficult to treat. So if we could efficiently manage the beds in the hospital and streamline the flow of patients through the hospital, then we can potentially mitigate some of this. But we need to know how long the current set of patients are going to remain in the ICU if we're going to be able to come up with some sophisticated strategies to plan ahead. So the remaining length of stay problem for us means that we take a patient's stay in the hospital. So on the left, you can see this is where they arrive in the unit, and then they'll be discharged at some point later in the stay. So most patients will be discharged from hospital and will go back home or go to a different ward. And then some patients will die in the ICU as well, because the ICU itself has quite a high mortality rate. So at any point during this length of stay that the patient is in the ICU for, we'll want to know, can we predict from the data that we have up until this point, can we then predict how many more hours they have left in the stay? And we need to be able to do this at any point during their stay, because at any given time, we're going to have a set of patients in the ICU, and they could be at any point within their length of stay. So it's super important that the model can adapt for that. And at the moment, the situation is that clinicians will tend to predict the length of stay right at the start of the length of stay, and then that doesn't get updated, even if there's an adverse effect on the patient. Like if the patient has some kind of problem, then it won't be updated. So it's quite a suboptimal system at the moment. So if we look at the things that we're actually predicting, on the left, this is showing the actual distribution of patients that come into the ICU, and it's showing the distribution of their total length of stay. So we can see that most of the patients are only staying for a very short period of time. And most of these people are people that have had some kind of normally high-risk surgery, and they're just admitted to the ICU just to make sure that we can monitor them carefully, make sure that they're recovering. Maybe if they've had some blood transfusions or they need some kind of ventilation, they might come onto the ICU. The rest of the patients, these are normally more complicated patients that are there more long-term, and these are generally the more difficult to predict. So if you look at the average coronavirus patient, they would be staying for about 7 or 8 days on average, or possibly much longer than that, because typically a big factor in how long they stay is how long they need ventilation for. So yeah, it's a very important problem at the moment. The graph on the right is showing what happens if you take the remaining length of stay. So this is the problem that I showed on the previous slide, where we can predict at any point during their patient's stay, not just right at the start. And we can see that this is very skewed, this distribution. So there's a lot more short length of stay than longer length of stay. And the reason for that is because if the patient stays for 5 days, at some point during their stay, they'll have less than half a day left. So this is why they're contributing to the shorter length of stay bins. Okay, so the data itself, the data we use is from an American data set called EICU, and it contains over 200,000 different ICU stays from many hospitals across the US. And the actual data itself contains many different things. One of them is time series. So these are parameters that vary over time. So this could be things like heart rate, the patient's heart rate, their blood pressure, and often these things are logged directly by machines because the ICU contains a lot of specialist equipment that often logs these parameters for you. The other thing is demographics. So these are different in that they don't change throughout the stay. So these might be things like age, gender, and ethnicity, and you'll need to process these in a different way to the time series. The next two things, so diagnosis and medications, these can be particularly tricky for machine learning to work with because they will tend to be, so there'll be a lot of them. So there's a lot of different possible diagnoses that you could have. And most of the diagnoses that you might have are very rare, which means it's very hard to get enough information about all of the diagnoses to actually process them effectively. And it's the same with medications. So you'll have some common ones like insulin for diabetics, but then you'll have a lot of very rare ones. And then finally, it also contains lab results, which are essentially time series. So they do change over time, but they tend to behave differently because they're sampled much more irregularly and they have much more missing data in between them. So this is an example of one patient in our data set. So the thicker bands that you can see here, this is the actual raw data. And the thinner bands underneath it is a kind of indicator of how recent that data point was sampled. So the color bar on the right kind of shows you what you're looking at. So the red values, these are values that are higher than average. And the blue values are lower than average, and 0 means the mean value. So we can see that respiratory rate and heart rate, these are automatically logged by machines. So we can see that often they're completely up to date. Maybe the patient was taken off their respirator between perhaps 70 hours and 76 hours here, but otherwise they're automatically logged. Then we have other variables like the non-invasive blood pressure. So this is sampled by nurses that go around the beds and will manually measure the blood pressure. So we can see that in this particular hospital, it looks like they sample it every couple of hours. But that's again quite regular. But then we have these other three variables, which are lab results. So we can see this is way more irregular, although there might be there might be a pattern towards here where they're taken once every 24 hours-ish. But we have to be prepared for this to be any kind of pattern. Oh, sorry. Okay. So the model itself, we want it to be able to extract both trends. So we want it to be able to tell how the patient's doing over time and whether that's changing, like is the patient getting better or worse over time. And the other thing we want to know is inter-feature relationships. So I mean things like the relationship between the blood pressure and the heart rate together. Because often when you combine different variables together, you get more something that's more meaningful than the original data. So one example of this is, again, relevant to respiratory patients. So two original features could be like, so the PaO2 here, this is the blood glucose level. No, sorry, the blood oxygen level. And FiO2, this is the amount of oxygen that the patient is breathing in. So the blood oxygen level might tell us, you know, how well oxygenated is the patient, and this can indicate how the lungs are doing. So sometimes if the lungs are failing, that will tend to decrease. But sometimes the blood oxygen could be high just because the patient is breathing in a lot of oxygen. So it is more helpful if it's normalized for the amount of oxygen that they're breathing in. So this is an example of where if you combine two features together, you get something that's more meaningful than the individual parts. And we can see that here, this is just a study from 2014 that found if you compare survivors and non-survivors in the ICU, the non-survivors have a lower blood oxygen level per amount of oxygen breathed in typically. So that can be quite predictive for us. Okay, so now I'm kind of moving on to the methods that we're using. So apologies if you're not so familiar with diagrams of networks, but I'm going to try and kind of give a higher level overview of what's going on. So along the bottom here, we have our time series. So on the left, this could be, so in blue, on the left, this could be the start of the time series. And then on the right, this is the position along which we're trying to make a prediction. So it's not necessarily the end of the patient's stay. It could be anywhere in the middle, but we want to be able to predict from that point onwards how many more hours they're going to stay in the ICU. So we can think of these arrows. So these are neurons, or artificial neurons in the network. And they're essentially just pooling information together. So we can see that all the points along this time series can eventually be pulled together to get one kind of summary variable at the top here. So this orange dot on the top right will contain a kind of summary of what's happened all through the time series. And that can be thought of as like a trend variable. So it's like summarizing how the patient's doing over time up until now. The other thing that we use in our model, so it's combining different convolution techniques. Pointwise convolution is where, so actually this diagram is showing the case for an image, because often convolution is used in images. But it essentially means that we take a single time point, so that's where the pointwise comes in. So instead of, in the previous slide I was showing pulling information across time, so sharing information across many time points. This is where we just take everything that we know from a single time point and then summarize it in some way. So this is where we're going to get those inter-feature relationships coming in. So that the kind of blood oxygen normalized for the inspired oxygen kind of things, because this network is then seeing all the information that we have at that one time. So that will contain all of those original pieces of information. So that will give us a summary of the patient's health state at one particular time point. The next thing I'll mention is these things called skip connections, which have become quite popular in recent years in the machine learning literature, because they tend to help you to train models quicker. But that's not really the reason why we're using them. So often, so neural networks will contain these weight layers which are stacked one on top of the other. And you can think of them as like processing units. So one layer will do some processing and then pass it on to the next layer, which will then process the output of the previous one until we get something that's some prediction at some point further downstream. But often when we're making these deep networks, it can be difficult for the network to learn something meaningful when it's got to go through all of these different stages. So the network then has an option of listening instead to a skip connection. So this skip connection just essentially just completely skips that part of the network and just passes whatever it was seeing before onto a much later layer of the network. And it's useful in machine learning because it makes the network shallower. But for us, with the temporal convolution, it gives us a special advantage. And so again, this is a picture of temporal convolution. So we can see on the bottom here, we have the time series. So the first time point in the patient's stay down to the prediction time. And in blue, we can see we're pooling information across time. But then we also have this connection in green, which is the skip connection. So if we decide for a particular variable, it's not useful to extract information across a long period of time behind it, then the network can just decide to just take the original data and not change it. And that's really useful because it means that the network can then modify its own, we say temporal receptive field, which basically just means how much time it can look backwards in time. And just to mention, that can be really useful when adapting to different features, because like I said at the start, we have certain lab variables which take a long time to change, as in they're only sampled maybe once a day. And then we have other variables that change much more short term. So the network can just adaptively change its receptive fields to suit each particular variable. Okay, so this is quite a complicated diagram of our model. So we apply these temporal and pointwise convolution in parallel. So on the left, we can see that these are our temporal filters. So they're just pulling information across time. So the one on the left, this is the one in blue, is just pulling information from before it for a particular variable. And then that will then be applied to each time point, and it will sort of scale along the time dimension. We can see that there's different colors. So there's a blue one and a green one. And what that's showing is that we assign different parameters to process each variable. And the reason for that is because we're essentially specializing the processing for each variable, because something like the heart rate might need different processing to something like blood glucose, for example. And then on the right, this is just showing that we're just taking all the information that we know about the patient at a particular time point, and we're putting it into the same processing unit, so the same layer, and then we're just getting the output, and then we combine the outputs. And this is just one layer of our what we call the TPC model, which stands for temporal pointwise convolution. And we actually do this 9 times, so many, many times over. The last thing that I'll mention about the methods is, so the loss function. So basically our task is a regression task. So what that means is we take a certain amount of information and we just distill it down to one number, which is the predicted number of days that the patient's going to remain in the ICU for. And usually we'd use something called the mean squared error as the loss function. So what that means is the error is just the difference between the prediction and the actual value. And then we square it so that it's always positive, and then we take the mean of that value. So the red line is showing the mean squared error. Now the problem with that is that, sorry, I should say the mean squared error for when the true value is actually 1 day. The problem with that is that it really does get very high. So we can see that this is going exponentially higher for long length of stays. So the model is going to be discouraged from predicting very high values. And also it's going to mostly get away with under predicting, because the mean prediction it's going to be producing is quite low because of the skewed distribution. So we found that this other function, so the mean squared log error, tends to be much better behaved. And I'll show you the results of that in a second. So to summarize why we think TPC is going to do well, so temporal pointwise convolution, it's been specifically designed to be able to extract both trends over time and the relationships between features. And it can also choose its look back distance, so its temporal receptive field, independently for each feature, because each feature has its own specialized processing. And the skip connections allow us to do that choosing between temporal receptive fields. So these are the results. The median couple of bars here, this is just showing a model which will always just predict the median value. So it's just a static model that always predicts bars that you're looking at. On the left is the mean squared log error, which is the loss function that we are optimizing for. And on the right, this is a more interpretable metric, which is just the mean percentage error that you're wrong by on average. So LSTM, this is channel-wise LSTM and transformer. These are all established time series methods, and TPC is our model. So you can see that our model is doing a lot better than the sort of more traditional time series models. And the reason for that is just because we've designed it specifically to work on these electronic health record time series data. If we look at why, so this set of experiments is just to break down why we think the TPC is doing so well. So if I just, so the TPC is on the left here, this is the full model. Then we compared to a model temp, so the third from the left, where we just took out the pointwise branch. So instead of having that in parallel, we just have temporal. And we find that already that's doing quite well on its own. So the temporal section is really what is giving most of the performance here. The pointwise on its own, so point, isn't doing that well, which isn't really surprising because it doesn't actually, so on its own, remember we said it only processes one time point at a time. So it can't actually look at anything. Without the temporal branch with it, it can't actually process any information across time. So I should say the baseline methods are doing around 110 on the right axis. So already everything above that is doing worse than the baseline. So pointwise on its own is doing worse than the baseline, which isn't surprising because it's not a time series method. On the right-hand side, we can see the temporal pointwise convolution with mean squared error. So we can see that it's performing a lot worse in general, and this was across many different metrics. And the only one that it did better on is the mean squared error, which is to be expected, and it only did slightly better on that. So the mean squared log error really does seem to give us better behavior. Yeah, just to quickly mention that the temp WS here, that's the weight sharing. So that's where, remember I said that we have specialized processing per feature. If we then take that away and don't make the processing specialized, then it performs a lot worse than if you allow it to specialize the processing per feature. So I'm comparing temp with temp WS here. Yeah, the other ones are just showing the effect of taking out the decay variables, which was the indicator variables that I showed you in the thin strips underneath the single patient example earlier. This was just a visualization that we did, because when you get the prediction of the length of stay, there's two other things that you know at the time. So you know what the prediction is that you just got. So that's on the y-axis here. And we also know how long they've already stayed in the unit for. So this is just showing the mean absolute deviation, so the the absolute amount at which you're wrong when you're predicting. And we can see that when the predicted remaining length of stay is low, so when it's saying the patient's going to be discharged soon, so that either means the patient's likely to die in the next day, or they're likely to be moved out of the ICU. So this makes sense that this is a lower error, because these patients are either looking well or they're looking like they're not going to make it for the next 24 hours. The prediction gets harder the longer that they're likely to stay, and also the longer that they've already stayed. Because if they've already stayed for a long time, that identifies them as one of those long stay complicated patients, which I mentioned, like there's a lot of patients that are just surgical patients that are easy to predict. And then we have the longer stay, more complex patients. Okay, so that is most of what I wanted to talk about. And yeah, I wanted to thank my funders and also my supervisor, Pietro, and Stephanie Highland at Microsoft. So yeah, I'm happy to take any questions that anyone has.
Thank you very much. Thank you. That was an interesting talk. Yeah, Tani, do you have any question?
Yeah, I have one. Let me just think of how to phrase it. So from what I understood, basically you have these networks that come up with predictions of how long people's ICU stay is, which seems very useful. Would people find it useful to have like very good uncertainty estimates of the predictions, or is that not so important?
So we didn't come up with uncertainty on an individual level. What we did to work out the model uncertainty here is we just ran it, trained it 10 different times, and looked at the test error. One of the things that we did look into, which, am I still sharing my screen? Am I still sharing my screen?
Yep.
Okay.
Yes.
One of the things that we did look into was the aggregate performance, which gives a bit of an idea of that. Yeah, it might allude to your question anyway. The answer to your actual question is we don't have an individual uncertainty because we haven't done, we probably have to use some kind of Bayesian approach for that. But one of the things that we did do was so one of the things that's important when it comes to bed management isn't just individual uncertainty, it's actually the uncertainty overall when you look at all the patients currently in ICU. So what we did was a simulation study where we randomized 16 patients from our data set that were going to be in the ICU, and we did this 500 times, and we looked at the true number of people that would still be there after 1 day, 2 days, 3 days, 4 days, 5 days, etc. And we can see that it falls off from 16. And then we looked at our predictions, and we found that in general it was fairly well calibrated. But after 1 day, our model does slightly underpredict the number of patients that will still be there. And in terms of the error, this is your uncertainty around the error. Well, I guess it's not really the uncertainty, it's like this is the standard deviation of the error that we have. So I guess you could expect it to be roughly within one patient also, like, yeah, of the true value most of the time. Does that kind of answer your question?
Cool, yeah, I think it answered a more interesting question, I think, than I was asking, so that's nice.
Okay, well, the answer to your actual question is just no, we haven't modeled individual uncertainty, but I think for the bed management application, it's not like clinicians are going to be actually using these on an individual basis. It's more just the question that we want to know is how many beds will be available in the next day, and the day after that and the day after that, because then it can enable us to do more sophisticated planning. So things like, if we know that we've got a bunch of patients that need a high-risk surgery, but it's elective, so we can decide when we want to do it, it's not an emergency. If we predicted a lot of long-stay patients in the ICU at the moment, then it would make sense to not send a lot of people into high-risk surgeries, because we're going to hit capacity. And at the moment, that's a big concern, ICU capacity. But even in normal scenarios, most ICUs are operating around 90% capacity over the winter. So, yeah.
That was actually the question I wanted to ask, because I was like, how would governments around the world use this to sort of predict the amount of bed space they'll be needing for the pandemic? But you sort of answered that already. Yeah, so I really do think that this is a very relevant talk at this time. And I do hope that probably the papers should go out there very soon and let people who really need this get to see it, because it will be a lot of help at this time of the pandemic.
Well, I've submitted it to the Machine Learning for Healthcare conference, and I should hear back on the 19th of June for that. And I'm also submitting to the ICML healthcare systems workshop. So, I mean, hopefully people should hear about it relatively soon.
Yeah. Well, thank you so much for that very brilliant talk. Thank you so much. And we're very grateful that you took up this talk at very short notice. Yeah.
Oh, no worries.
Yeah, thanks. And thanks for all those who could make it today as well. Yeah, so hope to see you next week. Thanks. Bye.
Thank you. Bye.
Bye.